Welcome back to ECE 220. Today we're talking about sources and resistors. We've been mainly dealing in general terms, talking about power and energy, current and voltage. Now let's look at some particular elements that might give rise to those. That's now what we're doing in Chapter 2. Where do these things, how are we going to create these in the lab? How are we going to work with them in our analysis? What can we now start working with and start saying, oh, this particular element does have a current and a voltage associated with it, so now we can talk about those two variables. We can talk about power, we can talk about energy. As announcements, passport assignment is due Saturday, as is homework number 0. Thank you. I'm having a resistor returned to me. I was maybe kind of hoping it would get lost, but it might get lost on the desk before or as I leave today. But if not, it will remain on my desk for another year or two. Who knows? Homework number 1 has been made available, and that's due on Tuesday following your long weekend, correct? So what we have, I think you already have the information you need to work homework number 1 in terms of what we've talked about in class. Now we're in Chapter 2, and that will be all or partially in homework number 2. You'll have a third homework assignment prior to exam number 1. Homeworks 1, 2, and 3 will be the material that you'll be responsible for exam number 1. Just as a precursor. As I said to begin with, now let's talk about some of these particular elements that we can now think about specifically when we're dealing with currents and voltages, power and energy. And we'll start with sources, which on a grand scheme, that's the power company. They provide us with a lot of source of our energy that we are wanting to use. But in this class, you may be dealing with a desktop power supply, something that you now can connect to produce a voltage source or a current source, and as we model those, we will treat them as ideal sources. We'll also talk about what is a permitted and a non-permitted, or a valid and invalid interconnection of sources. Then we'll talk about dependent sources, meaning now we can have current supplies and voltage supplies that actually depend on different variables in our circuit. And these might arise in this class in operational amplifiers in Chapter 5. That's a way of actually giving you an example of a dependent source. In the beginning of the class, we'll just draw a symbol. So now when I say dependent source, you might be thinking diamonds. When I say independent source, you might be thinking circles. But those are the symbols that we use, and we'll just create some dependent sources, independent sources, and you'll now be forced to analyze those circuits containing those devices or those elements. But in fact, behind the scenes, to actually create that in practice, one way is via a op-amp, an operational amplifier. That gives us a way to get a dependent source. Other dependent sources can be with transistors, and that's now a follow-on class to this one. ECE 351C, you talk about transistors. Well, here we can simply say, oh, let's just create a model of how it's going to behave, and we can do the analysis based on the model. In the class after this, in 351C, you'll understand more about why that model is what it is. Here we'll just say, here's a model, and we'll plug it in the appropriate way. Once we've talked about sources, independent and dependent, we'll say, what's our first element? And we're all one of these, right? We're all one of those squiggly lines. Now, after yesterday's class, we all know that we represent R equal to 100 in terms of, well, if we had 1 amp flowing through there. Well, we'll learn about the formula for that. But anyway, we are a resistor in terms of if we wanted to now model the thermal behavior of this classroom, I could now draw an electrical circuit and say, oh, this is what the power is that's necessary to drive this particular model. And now I maybe say, what kind of cooling capacity do we need to accommodate that thermal load in our system? Ohm's law, V is equal to Ri. You've probably seen that in physics, didn't you? Or IR. So that's Ohm's law. And ideally, it's a linear relationship, but that linear relationship is only valid over a finite interval. And so we are going to try to force ourselves to work in that linear operating range where V is equal to Ri. If you get beyond that, then our models don't work, and we have inconsistency with what we're trying to model and analyze with what's happening in reality. But knowing when those break down is what we will need to figure out. And we'll do that based on figuring out power formulas for resistors. Can we now describe the power absorbed or consumed by that resistor in terms of the resistor value and the current, or the resistor value and the voltage? We'll have two formulas. We'll look at different limiting resistor cases and permitted and non-permitted source interconnections based on now having a resistor that has a resistance of 0. That's now just a pure wire, and we'll call that a short circuit. Or a resistor that has an infinite value, and now that's basically nothing there. That's an open circuit. Those are the limiting values of resistors that we can talk about or think about when we're analyzing circuits. So let's get started. Ideal sources. In parentheses, I'm saying when I say that, you might start seeing, well, maybe what I should have done is move this. Let me move this down virtually. What I'm really getting ahead of myself, this was supposed to go here. Ideal sources can be independent or dependent. When we say independent, think circles. That's what I'm illustrating here with an ideal independent voltage source highlighted in yellow. That's the ideal independent voltage source. It's interconnected to a generic load, where the load is just a box. But that load now we can say has a voltage across it and a current that's being delivered to that load circuit. In this interconnected structure with an ideal independent voltage source, you have certain properties. And I've tried to bullet those out. One of those is that source voltage, if you say now in the lab, I want this voltage source to be 10 volts, you'll now set it at 10 volts. And if you don't have any limitations on the way that you've adjusted the knobs, that will supply 10 volts no matter what you hook up to it. That's ideal. Obviously, there are practical limitations. If you hook something to it that it's drawing so much power that it can't support that 10 volts that you're trying to make it have, then it won't work. But ideally, the source voltage, V sub S, is constant for any valid load circuit that you attach to that source. And if we just had I equal to 0, that's okay. What's I equal to 0? No current flowing. What would that mean? What would that look like? Well, that means there's no load connected. We've simply disconnected. If we had nodes A and B, we would simply remove that load circuit, and that would give us an open circuit, and I would be 0. And that's okay for an ideal voltage source. We're also assuming with an ideal voltage source that the value of that current, I, is determined by the load circuit. But that supply will provide us with whatever I is needed, depending on how we connect it. Also, the value of V sub S is going to stay fixed at the constant value that we set it at, independent of what I is requested. Whatever the load is, if we say we have an ideal voltage source of 10, it's going to be 10 no matter what we connect it to. The other restriction is that that current needs to remain finite. That's the restriction on the load. If we now tried to summarize those properties of an ideal voltage source in sort of one sentence, we could maybe say the voltage of our ideal voltage supply, V sub S, is maintained regardless of the finite value of being supplied by the source. How do I fill in the blank? What goes in the blank if V sub S is maintained regardless of what? No matter what the current demand is. What we need to then fill in here is I. The voltage of that ideal voltage source is going to be whatever we want, 10, 5, 6, however we set it. But once we set it, it's that no matter what we hang on to it, as long as I remains finite. We don't want I being infinite. Current source, ideal, is very, well, we'll describe it consistent with how we've described the voltage source. But now, what do you think is going to be maintained? I sub S, no matter what that voltage is across the load circuit. In an ideal independent current source, again, think circle. That's a circle with now an arrow through it. And the value of that ideal source is I sub S. That source current I sub S is constant for any load that we connect to that source. That's the ideal independent current source. Which means now a voltage of 0 is okay. And as we'll learn with Ohm's law, voltage is R times I. If that load circuit had a resistance of 0, then the current would be, the voltage would be 0 because the current I times 0 is 0. So having a wire for your load circuit is okay with an ideal current source. And we'll learn that if we flipped those, that's what's not okay. We can't open circuit this current source and we can't short circuit a voltage source. Those are not permitted. But here I'm giving you what is okay or what's acceptable. With a current source, the value of the voltage across that load circuit is going to be whatever it is based on what that load circuit consists of. However we've built the load, that's going to produce some V, and it doesn't really matter to the current source. The current source is just going to be giving you 2 amps. Is that a question, or are we exercising?
So the biggest difference between these two circuits is that one has a constant voltage being supplied and the other has a constant.
Yes, so the difference, the distinction between these two ideal independent sources is one's a current, one has an arrow, one's supplying a constant current, and the first one is supplying a constant voltage.
Okay, and that's when you're talking about ideal power source, just so like a power supply voltage and current.
So now if you have an ideal voltage source What that says is the voltage is fixed at whatever you fix it at, and the current, that source is ideal, so it'll give you whatever current is necessary to maintain that voltage. So if you had a 9-volt power supply, it's going to stay at 9 no matter what you hang on to it.
And you can have other devices that you set the current and voltage will change.
And now you can have in the lab, you're going to have a power supply that is really a voltage source, but you can fix that to give you a constant current, and then you can have not an ideal, but a current source in the lab. It's going to be a practical current source. Yes?
This might seem silly, but how does that current remain the same even once you increase resistance and loads?
So the question is, how in the world does it keep giving the same I if we change the load? The first word, ideal. It doesn't care what you hang on to it. If you say, give me 2 amps, it's going to give you 2 amps. That's how you've designed it. So inside that box is the circuitry that doesn't care what you hang on to it. If you set it now at 2 amps, it's going to give you that 2 amps whether your load is 1 ohm or 1,000 ohms. It's going to just keep giving you 1 amp. And that's how we will use it when we start designing or analyzing these circuits. If we say, oh, we have a current source, we know exactly what the current is that's coming out of that source. We're going to assume it's ideal. Yes, it's going to have to do more or less depending on what you hang on to it, but it's going to give you the 2 amps or the 3 amps, whatever you specify. Where were we? So the voltage depends on the load circuit. The voltage will obviously be different if it's 1 ohm resistor or 1,000 ohm resistor, but the current's going to be the same. That's what the third bullet is trying to say. The current being supplied by that source is not influenced by the value of the voltage V, or it's not influenced by the load circuit. Whatever you're asking of that current source, it's going to give you. Granted, all of that assumes that V is finite. If V goes to infinity, no, we no longer dealing with the ideal current source. Here, if we try to summarize those bullets in one sentence, the current that's being delivered to our circuit by that ideal current source is maintained regardless of the finite value of what across the terminals of the source. And now if you really didn't know the answer, you could kind of be clued in by, you know, when you're learning how to read, they always say, well, interpret it based on the context. If I knew the context, I'd know what I was reading. Anyway, what's the what are some key words around this? Across. What's an across variable? An across variable is a voltage. We measure a voltage across a resistor. What's a through variable? That's the current. Here, what's cluing in to what should be in the blank is a finite value of something that's across the terminals of the source. Well, what's across 2 terminals is a voltage. A current is not across 2 terminals. A current is through an element. In this case, then, we can complete that sentence by saying that, whoops, the voltage, it doesn't matter what that voltage is, as long as it's finite, I sub S is going to be maintained on that ideal current source. All right, you decide. Is the following permitted or not permitted in terms of an interconnection? Suppose that now I go ahead. What in the world? Oh boy. Suppose I do that. I have two ideal sources and I connect them together. I have a 20 volt source and a 5 volt source. Is that permitted or not permitted? Based on the definition of the ideal voltage source. These are now voltage sources. All right. How many think it's permitted? How many think it's not permitted? So now it's actually not permitted because we can't force A to be at two places at the same. How do I want to say this? A can't have two values and still be 1 point, in a sense. So you can't have 5 volts, and 5 is not equal to 20. You can't force one voltage supply to be at 20 and another one to be at 5 and expect them to be compatible when you connect them together, because 5 is not equal to 20. 20 is going to try to give you 20 no matter what. 5 is going to try to give you 5 no matter what. That doesn't make sense. So this is not a permitted interconnection structure. This is now invalid or not permitted, because you can't have 5 equal to 20. Let's look at another one. Permitted or not? Is that permitted or not permitted? 20 volt supply with a 20 volt supply connected from negative to positive in the same way. Now we're trying to force A to be 20 and 20. That's fine. Now each supply won't necessarily have to maybe work as hard, but here 20 equals 20, that's good. We comfortable with that? Yes. So now would the second power supply have to be negative? By that, are you saying, does it need to be, oh, let's see, how do I want to say this? Are you wanting to do that? So now what does that mean? We're going to learn Kirchoff's voltage law, which essentially says that if we walked around and if we viewed these potentials as if it was like altitude or elevation, if we walked up 20 flights of steps, then what's the next one say? Walk up another 20 flight of steps, because I'm going from lowest to highest, and now am I back where I started at B? No, I'm 40 steps up, not at 0. So in fact, that's the incorrect labeling of the polarity. We need to be, if we start at B and we go around that path, we better end up back where we started when we get back to B. So what is allowed is this. So if I use my stair climbing analogy, I would go up 20 steps. Shouldn't have labeled it 20 because I don't have 20 steps to go up. And then what happens? Then as I reach A, now the right side, I go down 20, and now I'm back at B. So A is at the same potential, the way that the labels are placed presently in that picture. And that's a permitted or a valid interconnection. Now I'm dealing with current sources. Permitted or not permitted? Permitted or not permitted? Oh man, he was walking upstairs. That was across. Now he's through. Now he's doing through variables. Now look at A, and essentially what you're trying to do is say, in this case, how much charge is flowing into A from the left? Is that the same that's flowing out to the right? That's one way of sort of thinking of that, and if that's what you're asking your sources to do, then it's okay. Here, if you look at A, you have point A, node A, you have 2 amps coming in from the left, and how many amps do you have going out to the right? 2, so it's consistent. This is okay. This is permitted. So this looks just the opposite of going upstairs and downstairs. Now the arrows are going in the same direction, in a sense, around, and that's okay. That's what we want with current sources when they have the same values. Is this okay? Is this permitted or non-permitted? Not, because now you're putting 2 in and somehow 4 is coming out. That's not making sense. So now the current supply on the right is saying give 4, push 4 through, and the one on the left is say push 2. Those are not going to be compatible. This is not permitted. What about this one? Permitted or non-permitted? How many think it's permitted? Why? Okay, the explanation is both are finite. The 20 volts will supply whatever current needs to be supplied, right? And the current supply will supply whatever voltage is being requested. So in fact, it is permitted, but it really wouldn't even matter if I would change this to that. That would still be okay. That supply would still be trying to push 3 amps, and it will give you 20 volts from, I don't have it labeled, from A to B. So either of those would allow for this to be permitted. So I don't know that it really matters, so I'll just leave it. Let's say that one's now permitted. Because you're not asking one or either one to do the impossible. Now they are compatible. The power supply and the current supply can be interconnected. Yes? In which one? In number 3, if I switched the arrows, or can I do this? Or now you're basically saying, well, let me do what you requested initially. You said, can I do that? And is it permitted? Is this now permitted? Now I have what? I have, well, I'm getting ahead of myself in the explanation. This will violate Kirchoff's current law. Now what would we have? We would have 2 amps coming in and 2 amps coming in, and there's nothing going out. So now we're accumulating charge at that node, and we can't do that. So this one, to be consistent with what I was trying to, I think, that's how we started. I better leave it that way. So now this one. So now we're not worrying so much about the currents, are we? The currents now, we're just saying these supplies will produce the currents necessary to give me 20 volts and 20 volts left and right. The current direction doesn't matter. And so this is ideal. The question was, this is just for ideal. Yes, it's just for ideal, but most of this class, we're assuming ideal conditions. In the lab, you're going to have practical scenarios, so your sources may not just be a pure voltage supply. You may say, oh, there's some internal impedance, so you model that as a resistor. But we're assuming when we start modeling, this is the ideal behavior of our source. Dependent sources. Now see or think diamonds. Now our symbol to represent dependent sources will be this diamond shape. But it's still, in this case, it has polarity labels. It is a voltage source, but in this case, it's a voltage-controlled voltage source. V sub x is some variable that exists somewhere else in our circuit. And it's now controlling the voltage across this particular element. And it's scaled by this scaling factor mu. This is now what somebody might call a VCVS, a voltage-controlled voltage source. Somewhere else in the circuit, let's say mu is 2. And let's say somewhere else in the circuit, V sub x is 5. What's this dependent source's value? Mu was 2, V sub x was 5. Somewhere else in the circuit, what's the value of that voltage source? Not 25, is it? It's 10. It's 2 times 5. If V sub x happened to be 4 somewhere else in the circuit, mu's still 2, what's that voltage? 8. It's dependent on V sub x. Whatever V sub x is, somewhere else in your circuit, you'll have to know where that is. That influences what the value of that source actually equals. This is a dependent source. And in this case, it's a dependent voltage source. And even more descriptive, it's a dependent or a voltage-controlled voltage source. Now, do you see all the different possibilities we can have? Can you name this one? Name this dependent source. What kind of a source is it? I heard current. Did I hear voltage? We have polarity labels, right? So eventually it's going to supply what? At its terminals, what's it going to be supplying? Current or voltage? Voltage. It's a polarity labeled source. This is going to be a voltage source, but it's a current controlled voltage source. So this one now is a current controlled voltage source. And if we used, well, here it's just tradition. Current is I, current controlled voltage source. So somebody might say, oh, you have an ICVS. Now you can go home and you can text this. Don't do it in class, but you can text this when you leave. You can say, oh, I have an ICVS. And everybody in this class will know what you're meaning, right? Oh, that's a current-controlled voltage source. I know these texts get pretty cryptic, but what are the units on rho? You now have I sub x, some current in your rest of your circuit. It gets scaled by rho to produce a voltage. So the units on rho have to be volts per amps, which we'll learn is ohms. So You could sort of think of rho as a resistor. All right, you did so well on that last one. What's this one? What's the eventual source producing? Voltage or current? Current, because it's indicated with a through arrow. So this is a current source. And what controls that current source? A voltage. So this is now a voltage controlled current source, and now we would say, oh, that's a VCIS. Did anybody see the last episode of VCIS on TV? I don't know. Oh, it's NCIS, isn't it? Oh, my bad. VCIS, voltage controlled current source. I don't even know what that show is. But anyway, 4. What's this one? Eventually, what is the source giving us? Current or voltage? It's a current source. And what's controlling that current source? A current. So this is now a current controlled current source, or that's now an ICIS. Now, if you liked the last game we played, let's do another one. But now we're interconnecting independent sources with dependent sources, and suppose, let me see if I can get this the way I want it. Suppose now that we say this is now 8 V sub x. Is that permitted, valid, or is it invalid or not permitted? I'm assuming now the independent voltage supply has a value of 2V, and that's what is V sub x in this circuit. I said before that V sub x or I sub x was some variable somewhere else in your circuit. Well, there's the somewhere else. Now you have V sub x is 2. Is this valid or invalid? Show of hands, how many think it's valid? How many think it's invalid? How many are not thinking? This one's valid, isn't it? Because what's actually happening? You now have 2 sources. What's the current source going to be producing? 16 amps, and the voltage source is set at 2. That's okay. Those can do that. They can play together. What about the next one? Suppose now I sub x is 1 amp, and this is 5 I sub x. Valid or invalid? Are these consistent? The current source is saying, whatever happens on the other side of this circuit, I'm going to give you 1 amp. What's the other side of the circuit saying? I'm going to give you 5. Is that valid? No, these are not compatible. So this is an invalid interconnection. You wouldn't want to be connecting up your circuit to try to produce this result. This wouldn't be workable. What if we now had V sub x is 3V, and I'll label the polarity, and let's say this is now plus minus V sub x. Valid or invalid? Pardon? How many think it's valid? How many think it's invalid? This is similar to one of the previous ones where you were saying, well, now we're going up, let's say 3 stairs, and what do we do next? We go down v sub x, but what's v sub x? 3 stairs. So this one is in fact valid. And if you don't see it that way, the nice thing sometimes about circuits is you can stretch these wires or collapse them if you want. You could put that dependent source in the right leg or the right stem of that circuit if it wasn't visually appealing to you the way it's drawn here. Before, if you said it was minus plus and then it was plus minus, well, just bend that circuit around. Do you see what I'm trying to suggest? To where it looks like what you wanted it to look like before. All right, now I want to give you the challenge of create a valid independent source connected to a dependent source. And don't use one of the previous examples. So now, on your own, create a valid independent source connected to a dependent source. And if you've created one, share it with your neighbor or share each of yours with the neighbor and see what kind of different ideas you came up with, even though you're in adjacent chairs. Maybe you saw what I talked about earlier differently, or you have a different way of creating. I'm assuming there could be 60 different circuits that are correct. However many students we have, I'm assuming we have 60 students. Not that we had 100 students in here, and I'm only saying 60% of you are getting it right. It's 100% is what I'm hoping for. And can you now, discussing with your neighbor, convince each other that yes, in fact, what I've drawn is a valid interconnection? I'm guessing no one drew this one. Did anyone draw that one? Is it valid? And what can you do? If you have a negative somewhere and you don't like it, you could actually remove the negative and flip the polarities, right? So if we said, oh, let me flip the arrow and then it'll be I sub x, then I have 6 amps going from bottom to top and 6 amps going from left to right, and they're all compatible. So that's a valid interconnected circuit. Those are our sources, independent and dependent. And now you know how to text the 4 dependent sources to anyone you want, right? Let's now talk about this Ohm's law. Now we're going to run into like 3 Germans in a row. Here's George Ohm, a physicist back in the 18th century, late 18th century. That's his mugshot. He turned in his passport. It's due on Saturday. You know what he did this summer that was fun? Let's not go there. But here is Ohm's law. V is equal to Ri, right? And if we push it beyond, it may take more voltage to get a little bit more current, and it won't satisfy that linear relationship. So we're going to, in this class, be focused on that linear region. And depending on what R is, that slope obviously will change. It's traditional that you have an IV curve. If we looked at V is equal to Ri, we would be saying, oh, I is our independent variable and V is our dependent variable. But either way you slice it, you get V is equal to Ri. R can be an actual resistor, or it could be a model of something like us. We say, oh, model the thermal behavior of us. Oh, that's just going to be a resistor, like a 100-watt light bulb. Question?
Yeah. So at what point would we explore other calculations for linear region, like in classes?
So the question is, when would we explore those curved regions in this IV curve? In this class, probably not. Now, where you could is if you exceeded the power rating on your resistor. Most of our resistors in this class only have a 1/4 watt power rating. If you now expect that resistor to give you, or to operate when you're trying to push more than a 1/4 of a watt through it in terms of what it's absorbing, then you're going to get into those curved portions of this curve, and so we want to try to restrict ourselves to this linear region.
There are some other formulas that calculate.
Yeah, we're not going to need to worry about other formulas for calculating that curved shape and what that curved shape looked like. I guess maybe we can talk after the semester and you can produce some functions and curves with different resistors if we wanted. But in this class, we're just going to focus on the linear region. And his buddy, well, maybe they weren't buddies, but Ernst Werner von Siemens liked to write it a different way. He liked to think not in terms of 1/R, but in terms of G, Siemens. So we have G, I is equal to GV, conductance, Siemens, or the backward spelling of ohms, mhos. OHM is now MHO. That's the units on Siemens. If it comes up, if somebody goes, oh, I have so many mhos, you're going, there's a clinic down the street. They've got some antibiotics for that. Anyway, he was also an inventor, and that's his mugshot. We've already passed around a resistor just to give you a feel for what those might physically look like and how they might be constructed. Let's now talk about some limiting values of resistors, which we've really already talked about. If R is equal to 0, there's no resistance between point A and point B. That's now just a wire. There's no voltage drop across that. So in this case, we now have what is called a short circuit. And if we now said R goes to infinity, What does that look like if we draw that resistor between node A and node B? There's nothing in between. It's an open circuit. Was that your answer?
Yeah, but also
It's what? I can't hear you at all. I know. I'm joking. Yes, I really sometimes can't hear, so I shouldn't have joked that way, but the second time I did hear you, I realized you were saying, hey, buddy, time out. It's time to go. So let's just finish here. But I gave you more notes. Let me just stop by saying, now figure out on your own what these formulas might be for the power absorbed by a resistor, and start by finding the formula based on the passive sign convention and then Ohm's law. Combining those, and you can find two formulas for power of a resistor. We'll pick up there or somewhere tomorrow.